Hello, and welcome to Lesson 6, Part 1 on linear mixed effects models. Today, we will learn about linear mixed effects models, make figures for data for linear mixed effects models, and run some preliminary linear mixed effects models in R. Normally, we would also summarize our results in an R Markdown document. However, we won't be doing that today, instead saving it for Part 2 of this lesson. Okay, at the end of the last lesson, we had these questions. And I said that the answer to these questions would be linear mixed effects models, and furthermore, generalized linear mixed effects models. As always, let's start by going over the math. We'll start with our equation for a linear regression with two variables and an interaction. By now, this should be very familiar to you. Let's assume this is our equation from Lesson 5 on past US presidential elections, where X1 is the incumbent party, Democrat, Republican, and X2 is country in the Civil War, Union, Confederacy. Now, an ANOVA had the advantage of both including our two variables and accounting for other types of random variance, such as subject. So the main question is, how do we take this equation, but then add factors for random variance, i.e. the things we're not directly testing? Well, we take our equation above and turn it into this. There's only one new element to this equation. This A sub S variable is our random effect of state, S for state, which was our error term in the ANOVA. Now, you may notice that it's coded as A, which is the letter we used for the intercept of the model. And indeed, in a linear mixed effects model, you would say that state is included as a random intercept. What this means is that in addition to having a general intercept for the model, the value of y when x is 0, we also have intercepts specific to each level of the random effect of state, thus taking into account the fact that individual states may behave differently. So far, this is in many ways similar to our ANOVA, but what makes a linear mixed effects model so powerful is that we can include several different random effects. So I'm going to call this term random intercept number 1. And I'm going to add a second random effect of year. Recall that individual election years can also have different types of variance. And so by adding this term, I can get unique intercepts for each election year. With an ANOVA, we would have had to run two separate ANOVAs with different error terms. This may be more familiar to you as a by subject or by items ANOVA. But with a linear mixed effects model, we can include both terms in the same model. Now, one of the aspects of these models that I think people find most confusing is the vocabulary used to describe different parts of the model. You really have all the tools you need to understand what the model is doing, but it may seem more complicated than it should be since there's a new vocabulary being used. So let's go over an example. Think back to the baby chick dataset that we talked about a few lessons ago. In a write-up of the experiment, you could see something like the text here. In this paper, we tested the effect of time on weight. A total of 50 baby chicks were included in the study. Now let's gather our variables for this study. We have weight, time, and baby chick. And we'll see what each of these variables could be called in the language of an ANOVA and the language of a linear mixed effects model. For weight, it's actually the same. For both of these models, you would refer to weight as the dependent variable. However, after this, it starts to become different. In an ANOVA, time would be referred to as the independent variable. But in a linear mixed effects model, it would be a fixed effect. In an ANOVA, baby chick would be referred to as the error variable, but in a linear mixed effects model, it is called a random effect. Notice that in the linear mixed effects model, we have two types of effects, fixed and random, thus why it's called a mixed effect model. What I really want you to take away from this slide, though, is that you already understand all the parts of a linear mixed effects model. It's just a new vocabulary to describe the variables. So if you ever get confused, just come back to this slide for a reminder of what everything is. Okay, now let's go through each of the variables in our model. First we have yi, or a specific y value. Then we have a, the intercept for the entire model. Then as, the unique intercepts for each level of our random effective state. Then ay, the unique intercepts for each level of our random effect of election year. Followed by b1, the slope of our first variable. x1i, the specific x value for our first variable. b2, the slope of our second variable. x2i, the specific x value for our second variable, B3, the slope of our interaction, and EI, the random variance or the residual. As always though, let's see what this looks like a little more concretely with a figure. This is our data from the last lesson on ANOVA. Let's change the boxes into the individual data points though. Recall that for the ANOVA, we had to average over some variable, either state or year. But with a linear mixed effects model, we get to include all of our raw data points. So let's go through the equation now with the raw data. First, we have A. This is the intercept of the full model. Remember, since we have an interaction, this is the mean for the default level of both variables. In our case, Democrat incumbents for union states. And we see it's roughly 60%. Next, we have B1, which is the slope between our first variable given the baseline of the other variable. So the difference between Democrat and Republican incumbents for union states. Next, we have B2, the difference between our other variable given our baseline. So the difference between Union and Confederacy states for Democrat incumbents. I'm not going to go over B3 since so far all of this should be review, as we're just going over the math of a non-mixed effects linear model. But let's look at these data points a little more closely. As you can see here, I've tagged some of the points that are from the state Rhode Island. Now by adding our random intercept for state, we can make an intercept that is specific for data points from Rhode Island, as shown here, which looks to be about 55%. However, this intercept is different from another state, say for example Kentucky, which could have a lower intercept that may be below 50%. So by including a random intercept of state, we can fit unique intercepts for each state, in addition to a general intercept for all the data. We can do the same thing with our random effect of election year. Take for example the year 1964. For this year, we have an intercept that's rather high, but this will be different for a year like 2012, that may have a slightly lower intercept. Once again, we've been able to account for variance specific for each of our levels of our random effects. In the end, this gives us 3 types of intercepts: a general intercept for all the data, a set of unique intercepts for each level of our random effect of state, and a set of unique intercepts for each level of our random effect of election year. This is all great, but we're still talking about our dependent variable as a percentage of votes for the incumbent. And, at the end of the last lesson, we said it was bad to use percentage of votes as our dependent variable because it is based on count data. Well, yes, that's true. And with a mixed effects model, we can now analyze a categorical dependent variable, something that wasn't possible with an ANOVA. To show you what I mean, let's come back to our equation. Here's the equation for our linear mixed effects model. To analyze a categorical dependent variable, all we have to do is change the left side of our equation to look like a logistic regression. In the terms of a mixed effects model though, instead of being called a logistic regression, we call it a generalized linear mixed effects model. So now, instead of using percentage of votes as my dependent variable, I could have 1s and 0s for each voter for if they voted for the incumbent and run a generalized linear mixed effects model. However, I don't have that data, so for the sake of this example, I'm going to continue using percentage of votes. But if you have the original raw categorical data, it's always preferable to run a generalized linear mixed effects model and not to have to summarize the data. Okay, let's move to the first part of our actual R coding. To run linear mixed effects models, we'll use the R package LME4. As you see, our equation for a model with 2 fixed effects, including an interaction, and 2 random intercepts. The R code for this equation looks like this. Really, this should be mostly familiar to you from the LM call. Just instead of LM, we use the call LMER, since it's a linear mixed effects regression. If we're running a generalized linear mixed effects model, the call would be GLMER, like GLM. This will be discussed in more detail in the lab. Going through the equation, first we have our dependent variable, in this case percentage of votes for the incumbent. Next we have our 2 fixed effects, incumbent party and Civil War country, included as an interaction. Now, to add the random effects, we add it in a parentheses with a 1 and a pipe as shown here with state, and election year. Okay, let's take a look at what the result of this model is. The summary call will have more information than this, but the part you'll really care about is the fixed effects section, which looks like a linear model summary. First, we have the intercept estimate, which tells us the mean value for our two baseline levels of our fixed effects, Democrat and Union, given our random effects. Remember, this is still a linear model, so we need to take into account baselines when interpreting the estimates. Next, we have the estimate for incumbent party, then country in the Civil War, and finally the interaction of our two fixed effects. So far, this should all be pretty familiar to you based on your experience with linear models. This is why I want to stress again that you really have all the tools you need to understand these models. Okay, let's take a look at the random effects in a little more detail. To get these values, I use the coef call. The call will pull up values for both of our random effects, state and election year. As you can see, we have values for the intercept, and then each of our fixed effects, including the interaction. Recall that what we're really doing is saying we want to fit a different intercept for each level of our random effects. Okay, looking at the intercept for state first, we actually see that they're all the same. This can happen sometimes if the model finds a lot of variance elsewhere, and so the best fit has these all with the same value. However, for year, you can see that we do indeed get different intercepts for each level of year, as expected by adding year as a random intercept. One thing you need to be thinking though is, in ANOVA, we accounted for the fact that a variable could be within or between subject. Right now, with our random intercepts, that's not being accounted for, which brings us to part 2 of the math for today. Here's our equation thus far for a linear mixed effects model with two random intercepts. Just as we were able to have an intercept for the entire model and intercepts for our random effects, we can also have slopes for the whole model and for our random effects, as shown here. Breaking down this new equation, see here we have BS1 in addition to B1. This is saying we're adding a random slope for state by our fixed effect x1, or incumbent party. Similarly, we can add a random slope for year by x2, or Civil War country. Okay, let's go over all the pieces of the new equation. I'm going to go a little faster since most of this should be review. First, we have our dependent variable and our intercept, then our random intercept for our first random effect, and our random intercept for our second random effect, then our random slope for our first random effect, then our regular slope and the values for x1, then our random slope for our second random effect, and then our regular slope and values for x2, our slope for the interaction, and finally, any remaining random variance. Let's see how all this looks though going back to our figure. I've again highlighted the data points from one specific state, in this case Rhode Island. We've already established that each state should have a different intercept, as shown here. But now, by adding a random slope by incumbent party, we'll look at not just the data points within the baseline levels, but also in the other level of what our random slope is by, incumbent party. So, by adding a random slope, we're saying we want to build a specific slope for the fixed effect of incumbent party just for the state of Rhode Island, which would look something like this, and appears in our model here. Just as we in theory have a different intercept for each state, we'll also have a different slope for incumbent party for each state. Now note that we have a random slope of state for incumbent party, but not Civil War country. Just as for our ANOVA, we know we can't do that because a state can only belong to one Civil War country, so that is a between state variable. Similarly, year is only included as a random slope by Civil War country because a given year is either a Democrat or Republican incumbent election, not both. Okay, let's move on to the second part of the R code. Here is our updated equation with the random slopes, and here is the equation in R code. Again, most of this is the same. We have our dependent variable, percentage of incumbent votes, our two fixed effects, incumbent party and Civil War country, our random intercept for state, and our random intercept for year. For the random slope for state, we add incumbent party before the pipe, so that we want to add the random slope. By using 1 plus incumbent party, we say that we want to add both the random intercept and the random slope. Similarly, we have the random effective year and the random slope for Civil War country. Okay, let's take a minute to look at our new results. Overall, this looks pretty similar to our first model. We'll go over it in a little more in a minute, but let's take a look at our random effects coefficients. Starting with the intercepts for state and year, we now see that we do get different values for each level of both state and year. By updating our model with the random slopes, the best fit now includes unique intercepts for each state too. Moving to the effective incumbent party, we see that we get different values for each state, but not for year. That's because we added the random slope for state, but not for year. Similarly, for Civil War country, we get different values for year, but not for state, as we added a random slope for year by Civil War country, but not for state. Okay, let's take a moment to compare these models. First, we have our linear mixed effects model with only random intercepts, and then our model with both random intercepts and random slopes. Looking at the estimates, we see that they're almost identical. So by adding our random slopes made some difference, but nothing dramatic. Turning to our standard errors, we actually see that they've increased with our model with the random slopes. In the past, we talked about how within subject designs increase power and can reduce the variance, but that isn't always the case. Here we see that letting the model know that we have within state and year effects actually showed that there's a lot of variation within the various levels of our random effects, thus increasing the standard error. If this is confusing, that's fine. The main thing to know is that adding random slopes can change your model either in regards to the estimate, the standard error, or both. Okay, let's move to the lab for today. The data set for today's lab comes from real students who took the in-person version of this course. The experiment they completed was an online version of the Stroop task. So let's take a minute to talk about exactly what that is for anyone who's unfamiliar. In the Stroop task, you're given a color word and told to say the color of the ink, not the word itself. For example, here we have the word blue written in blue ink. So I would say blue because the ink is blue. However, here we have the word blue, but now written in red ink. So my response should be red. The first type of trial, where the word and ink color are the same, is called a congruent trial. However, the second type of trial, where the word and ink color are not the same, is called an incongruent trial. The second type should be harder to do, since you have to block the information of the text itself. Okay, so we have 3 research questions for this analysis. 1, are responses to incongruent trials less accurate and slower than to congruent trials? This is an effect that has been replicated many times, so we should hopefully find it in our data too. Next, we're going to split the experiment in half and see if responses are more accurate and faster in the second half of the experiment than the first, after participants have gotten a little bit of practice. And finally, we'll want to see if there's an interaction between these 2 variables. So for this analysis, we'll actually be building 2 models. First, a model looking at accuracy, which will be a logistic regression or a generalized linear mixed effects model. Our dependent variable will be accuracy, if they were correct or not. Our first fixed effect will be congruency, and our second experiment half. For our random effects, we'll have both the individual subjects who participated in the experiment and the individual items in the experiment. We'll go into more details about how to build our random effect structure when we do the lab. In addition to building our accuracy model, we'll also build a model on reaction times, which will be a linear regression. Our dependent variable will be reaction times, our first fixed effect congruency, and our second experiment half. And our random effects will still be subject and item. Pause the video now to do the lab. Come back to the video as suggested to learn more about the code in the lab. We start as we usually do by setting our old data frame to our to-be-created data frame. Our first new verb is rename. We use this to do exactly what it sounds like, rename a column. We simply set the new name we want equals to the old name. So simple RT block trial NR will now simply be trial number. We'll do the same thing for several other columns as well. Now there are several columns that we didn't bother renaming because we don't actually need them. So to make sure we only have the columns we want, we use the select verb. Within select, I write all the columns I want to keep and the rest will be dropped away, giving us a much cleaner data frame. Pause the video now and continue with the lab. This is our first time using the package ColorBrewer. The main call you need to know is this brewer.pal. It is used to make a specific color palette. Within the call, we first specify the number of colors we want, and then the name of the palette to pull from. If you were to then print out calls to the screen, it would look like this. As you can see, we have a list of 5 hex colors. To show you what they would look like, I've generated some fake data and plotted it with our 5 different colors, giving us a dark orange, light orange, white, light purple, and finally dark purple. I don't actually want all 5 of these colors though, I just want 2. But to get the extreme colors, the dark orange and dark purple, I had to request a palette with 5 colors. Now I want to save my 2 specific colors. First, I'll save the dark orange as my color for congruent trials. By saving the first element of calls, I save that first hex code that corresponds to the dark orange. Similarly, to save the dark purple for my incongruent trials, I'll save the 5th element of calls. Pause the video now and continue with the lab.